Hello class. So welcome to CHM 322 Organic Chemistry 2 class. This will be our first class in this course. This course is going to be taken by 2 lecturers, and part of it will be taken by me and the rest of it will be taken by another lecturer. Okay, in order not to take much of our time, today we are going to be focusing on stereochemistry. We are going to be spending at least 4 weeks on stereochemistry. And that begins with this module. So we are going to have 3 other modules where we'll be discussing other parts of stereochemistry. Now let's look at a brief review of isomerism. Whenever you hear the word stereochemistry, it is just an aspect of isomerism in chemistry. So for us to have a holistic view, I want us to look at it and make some reviews on certain things you already know about isomerism. Now, firstly, let me bring back to your memory what isomers are. Isomers are compounds having the same molecular formula but different structural formula. They have the same molecular formula but different structural formula. Now, isomers are divided into 2 major classifications. We have the constitutional isomers. The constitutional isomers are the isomers whereby they differ in the way they are connected. That is the carbon backbone. They differ in the way the carbons are connected. We call those ones constitutional isomers. And by now you have been taught that part of isomers. The isomers we are going to be paying attention in this course are the stereoisomers, which are the second classifications. They are subdivided into enantiomers and diastereomers, and then under diastereomer we have the configurational isomers, and then the configurational diastereomer, and the cis-trans diastereomer. The cis-trans diastereomer are also known as the geometric isomers. Now let's briefly look at constitutional isomers again, just to recap things you already know. I said they have different order of connection, and it gives different carbon backbone or sometimes a different functional group entirely. For instance, let's see the case having a different carbon skeleton. This here is called a isobutane. A isobutane is otherwise known as a 2-methylpropane. You can see 3 carbons, that's the propane, and then you can see methyl on carbon number 2. So we have this a 2-methylpropane. Whereas on the other hand, we have a butane. This is 1, 2, 3, 4. This is a butane. Now, if we look at their molecular formula, we'll see that we have how many carbons here? This is 1, 2, 3, 4. That means there are 4 carbons. How many hydrogen? 3, 6, 9 plus 1. That's 10. So we have C4H10. And also in butane, let's see, we have 1, 2, 3, 4. That's C4. We have 3, we have 5, we have 7, and we have 10. So that means we have C4H10. That means they have the same molecular formula, but they only differ in the way in which their carbons are connected. Okay, let's see the case of functional group. We can have compounds having the same molecular formula, but they will that do not only differ in the way their carbons are arranged, but can also differ in the functional group entirely. For instance, in ethyl alcohol and dimethyl ether, we can see a clear example. This here is 2 carbons, 6 hydrogens, and 1 oxygen. That is C2H6O. You can also see the same C2H6O, but they are 2 different compounds entirely because they have different functional groups. So different position of functional groups is also another possibility, whereby we have the same functional group, but the functional group are placed on different positions. For example, now this is a isopropylamine and this is a propylamine. Isopropylamine and propylamine only differ in the position of NH2. You can see NH2, the amine functional group is on carbon 1 in propylamine, but it's on carbon 2 in isopropylamine. Now, stereoisomers. In the case of stereoisomers, they have the same connection. They do not differ in their connection or their carbon backbone or in their functional groups. They have the same functional group, the same connection, but they differ in their spatial arrangement. they differ in their arrangement in space. So should peradventure you are asked to distinguish between the stereoisomers and the constitutional isomers, you will be expected to say the constitutional isomers, they have the same molecular formula, but they differ in their connections or sometimes their functional groups. But in the case of stereoisomers, they have the same connections, but they differ in their arrangement in space. We can see two major examples of stereoisomers. Like I've earlier said, we have enantiomers and we have diastereomers. The enantiomers are non-superimposable mirror images, whereas the diastereomers are all other isomers, all other stereoisomers. So whenever we have stereoisomers, we'll see that in examples. Once we are able to identify the enantiomers, which are the mirror images, every other one are all diastereomers. Once they are not mirror images, but they are stereoisomers of one another, then we call them diastereomers. Now, diastereomer also includes the cis, trans, and configurational isomers. The cis trans, I said earlier, is the geometric isomerism. Let's see some practical examples. We can see in lactic acid, and this is, we call this the R-lactic acid, and the S-lactic acid. I know you wonder what is R and what is S. Very soon you will get to understand that as we'll be naming different enantiomers in the next module. Now, we have R-lactic acid. You will see that it is connected to OH, CO2H, which is COH, the carboxylic group, the methyl, and the hydrogen. The same constituents are also found, the same attachments are also found around this carbon, meaning that they are identical in their connections. Their connections are all the same. They are connected to the same substituent. So what makes them different is that they are mirror images of each other and they are non-superimposable. We shall see what that means in a minute. Now, the diastereomer, on the other hand, they are also non-superimposable, but they are not mirror images. For instance, you can see that here we have our amine functional group on the right, and we have our hydroxy functional group on the right. But in the case of the other one here, we have our amine functional group still on the right, but our hydroxy functional group is on the left, meaning that they are not mirror images at all. They are not mirror images at all, but they are both stereoisomers. We'll see why they are stereoisomers shortly. Now, stereochemistry generally discuss about a particular property we refer to as handedness. Some objects are not the same as their mirror image. You know, there are certain objects that might be the same with their mirror image, but some are not the same with their mirror image. And technically, we say they do not have plane of symmetry. Any object that has a plane of symmetry will be the same as its mirror image, but some objects do not have a plane of symmetry, and as such, they are not the same with their mirror images. For instance, a right-hand glove is different from a left-hand glove. You see, you cannot put on your left-hand glove on your right hand, just as you cannot put on your right shoe on your left leg, because they have a property we call handedness. Likewise, organic molecules, including many drugs, have handedness. Many drugs, your cocaine, morphines, they have handedness. So we shall look at so many of them as we are going on. So, and we said that they have handedness that result from substitution patterns on sp3 hybridized carbon. Take note of the word sp3 hybridized carbon. It means that for this handedness to occur, it must be on a sp3 hybridized carbon. And we shall see what that means shortly. Now, enantiomers, which we say they are mirror images. Molecules exist as three-dimensional objects. Some molecules are the same as their mirror image. We've said that earlier. Some molecules are different from their mirror image. These are stereoisomers called enantiomers. So molecules that are different from their mirror image, molecules that are non-superimposable mirror images of each other are called enantiomers. So if you're asked to define enantiomers, enantiomers are molecules that are non-superimposable mirror images of each other. So let's see enantiomers and the tetrahedral carbon. Now, enantiomers are molecules that are not the same as the mirror image. We've said that. They are the same if the position of the atom can coincide on a one-to-one basis. we test if they are superimposable, which is imaginary. Now you can see we said it is imaginary because we are dealing with a plane structure, the one we are going to be displaying here. But in real life, these molecules are not plane. They have a three-dimensional structure. They are three-dimensional. So in order for us to really know that they do not superimpose, we have to see the three-dimensional structure, meaning that it's not possible for you to bring the two of them such that they will coincide on a one-on-one basis. That is, the hydrogen or whatsoever constituent present around the tetrahedral carbon will coincide one-to-one. So we shall see what that means again as we go ahead. This is illustrated by enantiomers of lactic acid. We've looked at that earlier. Look at this lactic acid again. You can see lactic acid here. We said this is one lactic acid and this is the mirror image of the lactic acid. Now, if we try to put them on top of each other, that means to superimpose them, we will see that they will not match. You can see we have your CO2H on this end and we're having your CH3 on this end. So it means we cannot put them one to one, although you can see the hydrogens are on the same level. We can see the OH, that is the hydroxyl, on the same level. But look at the CH3 and CO2H. You can see they are not matching. That's why we go to a mismatch. The same thing with this end. That means they are non-superimposable. Now, let's look at this also. Optical isomers of amino acid alanine. This alanine, now this is the mirror image of alanine. You can see this alanine here, and this is its mirror image. They are non-superimposable. So because of that, we call them enantiomers. The two images you can see on the screen right now are called enantiomers. Now, optical isomerism. Now, the question is, what is a non-superimposable mirror image? What is a non-superimposable mirror image? Like I said earlier, you can see now, this structure here is showing us a three-dimensional image of a molecule. You can see it is not a plain image. It's not just an image that is on paper. It's an image that is three-dimensional. Now, whenever they are non-superimposable, by the time I bring the mirror image of this compound, of this molecule, and I put it side by side, I will see that where the red color is here will be where the green color, or where the purple color, or where the yellow color of the other molecule is, meaning that they will not be able to match one by one. All right, let's look at examples of enantiomers. Molecules that have one carbon with four different substituents have a non-superimposable mirror images. Now, I said molecules with one carbon having four different substituents. Earlier, I talked about a sp3 carbon. The sp3 carbon is a carbon that is attached to four substituents. Whenever a carbon has four substituents, that means there is no double bond or triple bond in the carbon, but it has four different substituents. Not necessarily different. Once it has four substituents attached to it, it is a sp3 hybridized carbon. Now, when the sp3 hybridized carbon now have all the four substituents different, then it is going to have a non-superimposable mirror image, and as such, it will form what we call enantiomers. Now, build molecule model to see this. Let's see. In this case, this is a carbon. You can see it is attached to fluorine, to chlorine, to bromine, and to hydrogen. You can see all the four substituents are different. So because of that, its mirror image will be non-superimposable because all four substituents are different. If any two substituents on this carbon are the same, the mirror image will not be different. The mirror image will be identical to it, and as such, they will not be enantiomers. But in this case, you can see all four substituents are different, and because of that, they are enantiomers. The mirror image of this structure is non-superimposable. So that's what we have here. Look at, in this case also, we have fluorine, hydrogen, but we have two bromine. We have two bromine. You can see in this case here, the mirror image will look like this. But they will be identical because all I need to do is to turn this structure. If I turn it 180 degrees, it will look like this. And look at the two of them. You can see they are both identical. So the mirror image will be identical, and as such, they are not enantiomers. What is the big thing for you to take up from what I just said now? is that you look out. Every substituent around the carbon must be different. If not, that carbon cannot form a non-superimposable mirror image, and as such, they will not form an enantiomer. But if all 4 substituents are different, the mirror image will be non-superimposable, and as such, they will form what we call enantiomers. Now, mirror images, forms of lactic acid. Let's see. Okay. Now, mirror images, forms of lactic acid. We can see the lactic acid we've seen earlier. You can see we said they are mismatched. That means it is not superimposable. Look at the structure of lactic acid here in another form. Now, when the H and the OH substituent matches up, COOH and CH3 don't. And we've seen that when the OH and the H and the OH matches up, you can see the H matches. This is one lactic acid, this is another one. You can see the hydrogen matches up. You can see the OH matches up. But look at the CH3 and the COOH. And also, when the COH and CH3 coincides, the H and the OH don't. So there's no way you want to twist it. Whether we turn it 180 degrees or not, we'll still see that they are still non-superimposable. The reason for handedness, which is what we call chirality. What is the reason for handedness? Another way to call handedness is what we call chirality, chiral. Now, molecules that are not superimposable with their mirror image are chiral. That means they have handedness. Take note of that word. Molecules that are non-superimposable with their mirror image are chiral. A plane of symmetry divides an entire molecule into 2 pieces that are exact mirror images. Don't forget, earlier I told you that for us to have what we call handedness or chirality, technically we are saying that molecule does not have a plane of symmetry, or that object, whatsoever case it may be, that it does not have a plane of symmetry. Once it has a plane of symmetry, then it is not possible to have this property called handedness, which we are referring to now as what? Chiral. So a plane of symmetry, what do we refer to as a plane of symmetry? We said it divides an entire, a plane of symmetry is a line that divides an entire molecule into 2 pieces that are exact mirror image of each other. That means there is a way I can divide that molecule such that the 2 pieces will be mirror images of each other. If we have such a case, then that kind of molecule will not be an enantiomer. That means they will not have chirality center that we are talking about. Now, a molecule with a plane of symmetry is the same as its mirror image and is said to be achiral. So any molecule that is not chiral is said to be achiral. That means once it has a plane of symmetry, then it is achiral. That means it will not have chirality. We will see this one. We'll begin to look at the polarimeter and see how we measure chirality. Now, chirality, if an object has a plane of symmetry, it is necessarily the same as its mirror image. Take note of that word. Once an object has a plane of symmetry, I've mentioned that before, it means that object is the same as its mirror image. That object will be the same as its mirror image because of the plane of symmetry. And once a molecule is the same as its mirror image, you know that kind of molecule cannot be called an enantiomer because it is superimposable with its mirror image. Now, the lack of a plane of symmetry is called handedness or chirality. We are still saying the same thing, just looking at it from different, using different words to say the same, to pass the same information. Hands, gloves are prime example of chiral objects. They have a left and a right version. When you buy shoes, you buy the left leg and the right leg. You don't buy 2 left legs because there's handedness. They are not the same. That's the idea that we are passing across. So the meaning of plane of symmetry, let's see these 2 objects. You can see this cup as a plane of symmetry. If I should use this line to divide this cup into 2, you can see this half of the cup is the mirror image of the second half, meaning that the cup has a plane of symmetry, so it is not chiral. There's a way I can divide this cup such that both halves will be identical. But look at the hand. You can see the hand does not have a plane of symmetry. There's no way I will divide this hand into 2 such that this side will be the mirror image of this side. You can see what we have on this end is different from what we have on this end. So and does not have a plane of symmetry. That is, it is chiral, whereas your cup, a cup of this nature, has a plane of symmetry and it is achiral. The plane has the same thing on both sides for the flax. There is no mirror plane for the and. That's what I just explained. So chirality center at a point in a molecule where 4 different groups or atoms are attached to the carbon is called a chirality center. You see there's one of the slides I talked about asymmetric carbon. Asymmetric carbon is also the chirality center. The asymmetric carbon is a carbon carrying 4 different groups. And also, whenever we have a point in a molecule where 4 different groups or atoms are attached to a carbon, then we call that a chirality center. There are 2 non-superimposable ways that 4 different groups or atoms can be attached to one carbon atom. If 2 groups are the same, then there's only one way. A chiral molecule usually has at least 1 chiral center. Take note of that. Before we say a molecule is chiral, it means it has at least 1 chirality center. So if I give you a molecule and I tell you to tell me if this molecule is chiral or not, you must be able to identify at least 1 chirality center in that molecule. It can have 2, 3, 4, 5, and so on, but it must have at least 1 to be chiral. Look at this example. This is a 5-bromodecane. You can see I already stated it here that it is a chiral molecule. Now, how do I know it is chiral? You will check through all the carbons present in the molecule and see if there's any chirality center, that is a point in a molecule where 4 different groups or atoms are attached to the carbon. Let's see if we have such a case here. Starting with this first carbon, does it have 4 different groups attached to it? Obviously, no. We can see it has 3 hydrogens. This one too has 2 hydrogens, meaning that it already has 2 identical atoms. These 2 hydrogens already represent 2 identical atoms out of the 4 substituents of this carbon. This 2 hydrogen is not possible. 2 hydrogen is not possible to have a chirality center here. 2 hydrogens is not possible to have a chirality center. But look at this. Here, one, it is connected to this. This is one of the substituents. All this here, this is 1, 2, 3, 4. This is a butyl. This is a butyl substituent. Now this is a bromine substituent. This is a hydrogen substituent, and this is a 1, 2, 3, 4, 5, a pentyl substituent. So all the 4 substituents are different. So this point, you can see this asterisk, is used to represent chirality center. This point is a chiral center. This carbon is a chiral carbon, and this point is a chirality center. I hope you get the difference. We said this point is a chirality center, while this carbon itself is a chiral carbon. This carbon can also be called an asymmetric carbon, and it can also be called a stereogenic center. Put that in mind. We call it a chiral carbon, a stereogenic center, call it a asymmetric carbon. So there are differences between a stereogenic center and asymmetric carbon, but in every asymmetric carbon is a stereogenic center. So that's why we can use it interchangeably in this case. So that is why this molecule is chiral. If you check the other carbons, you will see there are no such cases where we have all 4 substituents different. So that is, so the substituent on carbon 5, you can see them listed out here, which we've stated before. That is why this carbon 5 is a chiral carbon. So let's see some worked example. Which of the following molecules are chiral? Identify the chirality centers and state the number of chiral centers in each. We'll identify the number of chiral centers we have in this molecule, and we'll state the number of chiral centers. We'll identify the chirality center, and we'll state the number of chiral centers or chiral carbons present in each of the molecules. You can see I used a fairly complex example to show you, because there are many simple examples I can show you, like the previous one you saw in the previous slide, this kind of a structure. But more often than not, you wouldn't be getting this kind of a question in an exam. You'll be getting more complex structures. So I want to use more complex structures for examples. so that you'll be able to catch it and understand it properly. Okay, now let's see the solution for the first one. Now I said all CH3 and CX3 carbons are not chiral centers. First, you need to put that in mind, that wherever you see a CH3 or CX3, why do I use the word X3? It means even if it is not hydrogen, whatsoever is there, if this was a CBr3, if it was a CF3, whatsoever is here, CX3, that kind of a carbon cannot be a chiral center. Again, all CH2 and CX2 carbons are not chirality centers. Automatically, it shows us that all this CH2 cannot be a chirality center. Once you see a CH2, CX2, now I use X to represent any molecule at all. Whenever you see a CX2, a CH2, or a CH3, a CX3, all these cannot be chirality center. Okay, and thirdly, all aromatic ring carbons are not chirality center. Let's see what we mean by that. Aromatic ring, when we say a ring is aromatic, we mean that we have a ring that is like benzene ring. In this case, this is our ring here. When we have a ring like the benzene ring, all the carbons in a benzene ring or similar aromatic compounds. In this case, this structure is not aromatic, but what we are trying to say here is that whenever you have cases where you have all these sharp edges, they cannot be chiral center, and we'll see why they are not chiral center very soon. So if you see, this is our conene. So therefore, there's only one chirality center, and it is here. For better understanding, let's look at the way it is solved. This is the same conene that I just showed you the solution. This is the structure that was drawn for you. But in the real sense, this structure is what we call a skeletal structure. If I draw a structure of this type, if I do something like this, in chemistry, we call it a skeletal structure. Any edge, any empty edge like this in chemistry represents a CH3. It represents a CH3 because every edge represents a carbon, and a carbon must have 4 substituents. So because it is at the edge, 3 hydrogens will represent the 4 substituents. The same thing with this, it will also have, this is also a CH3. Now, what about these edges? These sharp edges now, for instance, this place is a carbon. Every sharp edge is a carbon. And how many bonds do I have attached to this carbon already? This is 1, this is 2. It means there are 2 other bonds that we cannot see. So it means those 2 other bonds are also what? Hydrogen. So that's why we call it a skeletal structure. We do not show the carbon and the hydrogen. The same thing on this edge and on this edge. Now, let's go back and look at what we have in the case of our conene. Let me take this off. Now, in the case of conene now, on the other hand, look at conene. This conene is a ring structure, but one of the members of the ring is a nitrogen. That's why we are showing it. Once it is not a carbon, we must show what is in that place. Now, what will be in all these spaces? Now, look at it here. Instead of putting the ring and showing the skeletal structure, I have represented it with what is there originally. What is there actually in each of these edges is a carbon, CH2. Now, you can see there are no double bonds in the ring. So it means this carbon has only 2 bonds attached to it. The remaining 2 bonds are what are occupied by hydrogen. That's why we have CH2, 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 CH2. But look at this third one here. Instead of CH2, what do I have there? CH. The reason why it is CH is because you can see in this carbon, there's a carbon here automatically. There's a carbon at every edge. Now, this carbon is attached to 1 bond, another bond, that's 2, another bond, that's 3. How many bonds are we supposed to have around a carbon? We are supposed to have 4 bonds. So the 4th bond that we can see is hydrogen. Whether they show us or not, what will be there is what? Hydrogen. And that's why I have just CH here. So now, I told you earlier that whenever you see a CH2 or CX2, it can never be a chiral center. A CH2 or a CX2 cannot be a chiral center. So it means automatically all these parts are disqualified from being a chiral center. All these parts can't be a chiral center, they are disqualified. Let's look at this point. This is not a carbon, so it's also disqualified. Now coming to this part, this is a carbon, it is attached to a hydrogen, that's one. Is attached to all this. Now, in a ring structure, I cannot really tell exactly what is attached to because it is a ring. But all I can tell is that what is on this end is different from what is on this end. Do you agree with me? I believe you agree with me because here you can see the carbon attached to a nitrogen, then a carbon, then a carbon. But here it's attached to a carbon, a carbon, a carbon. So what is on this end is different from what is on this end. So it means the substituent here is different, the substituent here is different. This hydrogen making a third substituent, then all this makes the fourth substituent. So it means all the four substituents are different. Because of that, this point is a chirality center. This point is a chirality center. Now let's check the other carbons. You must check all the carbons both in the ring and outside the ring. Look at the ones outside the ring. Is this a chiral center? No, CH2. Is this a chiral center? No, CH2. Is a chiral center? No, because it is CH3. So how many chiral centers do I have in choline? I have only one chirality center in choline. Only one chirality center. I believe that is very clear. The second example is in menthol. This is the structure of menthol. I've already asterisk all the parts where we have the chiral center, but let's solve it together and see how I arrived at that. If I've given a structure, whether a ring or not, just pick a point to start. Pick any point. Let's start from outside the ring. Starting from this now, what do I have here? I said whenever you see a sharp edge in chemistry, if I see something like this sharp edge is a carbon. And all these endings that are not, you can't see what is there, they are also carbons. And because they have only one bond attached to them, it means they will have 3 hydrogens attached to them. Is that making sense? Okay, so we have CH3 on this edge. So it means on this edge, what I have is CH3. On this edge, what I have is CH3. Don't forget, CH3 can never be a chiral center. So it means it disqualifies these 2 carbons automatically. So I've checked this carbon, I've checked this carbon. Now to this carbon, this one is attached to 1. This carbon here, this is a carbon. It means on this edge, I have a carbon. You can see it's also attached to something else up here. So it means it has how many bonds? 1, 2, 3. So what will be the 4th bond? The 4th bond that we can't see there is the hydrogen. So there's a hydrogen attached to this carbon that we can't see. Now, this carbon looks like a chiral center because you can see that it has a substituent here. All these are a substituent. All these here are attached to this carbon, as you can see. It is also attached to a hydrogen, that's 2. It's attached to a CH3, that's 3. But look at the other side, we also have a CH3. So there are 2 CH3. Don't forget, for us to have a stereogenic center or a chiral carbon, all 4 substituents must be different. So automatically, this place also gets disqualified from being a chiral center. So this is not a chiral center, this is not a chiral center, and this is not a chiral center. Now let's move to the next carbon, which is this. Now, seeing this next carbon now, we can see it is attached to this one. It's attached to a hydrogen. You can see the hydrogen was shown. Even if the hydrogen was not shown, you should know automatically that once something is attached, a carbon is attached to only 3 substituents. The 4th one will be a hydrogen. So it is attached to 1. Or I said, or when you have a ring system, it is attached to this. So it means all what we have like this is attached to it. We cannot really define exactly what is attached to it, but we are sure that what is on this end is different from this end, because you can see here it is attached to a carbon, then a carbon before carrying this structure, and here is attached to a carbon carrying this structure. So they are definitely different. So this is a different substituent, this is a different substituent, this is a different substituent, and this is hydrogen, which is also different. So this point is a chirality center. So we found one. Then we can move on to the next carbon. You can see all these are different, all these are different. This is a hydrogen and this is OH. So this is a chirality center. This one is automatically disqualified because what will I have here? This will be CH2. Don't forget, I told you in a ring that does not have a double bond, once you see a sharp edge like that, that sharp edge is a CH2. And that is what we have here. So in this point, we have CH3, we have H, we have all this, we have all this. So it means there are 4 different substituents. So this is also a chirality center. This can't be a chirality center, this is CH2. This can be a chirality center, this is CH. So I believe we have checked out all the carbons. Okay, we've not looked at this one. This one is also a CH3, so it cannot be a chirality center. So how many chiral centers do we have in Mentor? Mentor has 3 chiral centers. Is it clear now? So that is how to find the chirality centers in a molecule. So what if I give you a structure that is not a ring? If I give you a structure and I draw the skeletal structure, I give you something of this nature, okay, and then at this end, I put bromine. On this end, I put bromine, and then I ask you to check for the chiral carbon. Now, this carbon here at this edge will be CH3, so it's not a chiral center. This CH2 is not a chiral center. 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 Now, look at this. This is 1, is attached to this 1, 2, 3, 4, 5. This is a pentyl, and it's attached to this 1, 2, which is a ethyl, and then it's attached to a bromine. What will be the last substituent that was not shown here? It is a hydrogen. So it means this point is a chirality center. This point is a chirality center. So do you see the way we identify chirality centers? But don't be fooled. When sometimes you can have a structure that looks like it's chiral, but it's not. Look at this, 1, 2, 3. 1, 2, 3. Okay. Now, if I draw the same structure now and I put bromine here, or I put fluorine or any other substituent, now you might be quick to say, oh, this is a chiral center because you can see a bromine. But take precaution. Whenever you see the structure, make sure you identify the other substituents around it. This now is a 1, 2, 3, which means this is a propyl. Look at what we have on this other hand. This is a 1, this is a carbon 1, 2, 3. This is also a propyl. It means this here is a propyl. This here is also a propyl. So automatically this carbon can no longer be chiral because it already has 2 substituents that are identical. Is that clear? So that is how we identify a chiral center. All right, now, so let's consider some practice questions. So at this point, all right, so let's see some practice question. So at this point, pause the video and answer each of these questions. Ensure you pause the video and try them out yourself. And then we shall look at it together. Okay, now let's see how to solve this question together. All right, the first one now, this structure here is a 2-chlorobutane. It's a 2-chlorobutane, and it's very obvious that this first carbon cannot be a chiral center because it's CH3. This second one cannot be a chiral center because it is CH2. But this third one, we have chlorine, that's one substituent. We have CH3 methyl, another substituent. We have hydrogen, is another substituent. This hydrogen is more like saying you are attaching a hydrogen is up here. So, but because we wrote it, this structure is called a condensed structure. So we just put the hydrogen beside it. The hydrogen can also be on top of it like this. So that means the hydrogen is also another substituent. And lastly, we have this is ethyl, which is another substituent. I mean, there are 4 different substituents around that carbon. So if we have 4 different substituents around that carbon, it means this carbon here, is a tetrahedral carbon. That means it is a stereogenic center or an asymmetric carbon. What about this one? It can be an asymmetric carbon because it has 3 hydrogen attached to this carbon. So the question says which of the following compound is has an asymmetric center. So this is one. This has an asymmetric center. For this one, the B, we know this cannot be an asymmetric center. This cannot be an asymmetric center. This, on the other hand, you can see we have CH3. This is a substituent. We have CH2CH3, that's ethyl. This is methyl, this is ethyl. We have hydrogen, that's 3. Then what's the third substituent? The third substituent is also methyl. So it means we have 2 methyl substituents. You need to take a good look at the substituent before you conclude. I know some of you might have identified this one to be a chiral center, but it is not because it has 2 methyl substituents. Let's look at the C for another example. We can see this is ethyl substituent. Of course, you already know this carbon cannot be a stereogenic center. This cannot be. So this is the one we are focusing on. All this substituent here is ethyl. All this substituent here is propyl. This substituent here is methyl. This is bromine. So automatically it means all 4 substituents are different. So this is a stereogenic center. For the case of this one now, let's see if we have a stereogenic center. This is one carbon carrying 3 hydrogens. It can be a stereogenic center. The second carbon is also carrying 2 hydrogens. So automatically this cannot have an asymmetric center. This O compound cannot have an asymmetric center. In the case of this, we know this can be an asymmetric center, or this can be. So it's this carbon we focus on. So what do we have here? This is methyl, ethyl, CH2CH3, ethyl, CH2CH3, ethyl. So we already have ethyl, 2 ethyls on both sides. Then we have bromine and hydrogen. Because we have 2 ethyl here, automatically this is no longer does no longer have an asymmetric center, and this carbon is not a chiral carbon. So let's look at the last one. This one here is carbon having double bond. Once you see a carbon with a double bond, automatically it cannot be a stereogenic center because that carbon is not even sp3 hybridized. A carbon having a double bond in between it is a sp2 hybridized carbon. And we said for us to have a asymmetric center or a chiral center, it must be sp3 hybridized carbon. So this is disqualified. This also have a double bond attached to it. This is disqualified. Let's move to this. This does not have a double bond. So this is attached to 1 hydrogen. It's attached to 1 CH3. This CH3, 1, hydrogen 2, NH2, amine, that is 3, and then all this structure. Now, do not say, oh, because the structure has a double bond, then it means it disqualifies this carbon. No, it is this carbon itself that must not be attached to a double bond directly, meaning that this carbon must be a sp3 tetrahedral carbon. So this carbon qualifies for that, and this is a substituent. This substituent is here, and this substituent is here, CH3. This one is here, different, and then hydrogen. So automatically, this is also a tetrahedral carbon. So the answer to this question is A, C, and F. I hope you were able to get the correct answers to that. So finally, before we leave, before we close for today, this is another more serious question, which is the kind of questions you should be expecting in your quizzes or your exams. You see, the question says tetracycline is called a broad spectrum antibiotic because it is active against a wide variety of bacteria. How many asymmetric centers does tetracycline have? So this is the question. How many asymmetric centers does tetracycline have? So we shall discuss this question. This is supposed to be, this is an assignment anyway. You have to answer it yourself. You have to take your time, study it and understand it. Then when we are having our discussion class, you can bring it up and let me know what was your challenge. Let me know your answers and I can help you to discuss it. So this is where we are going to end for today. So today we're able to summarize what isomerism is all about. We say it is divided into constitutional and stereoisomers. We went ahead to talk about enantiomers. We said enantiomers have non-superimposable mirror images, and for that to happen, they must have a tetrahedral, sp3 hybridized carbon, which has 4 different substituents. And we were able to check how to identify these carbons. So this is where we are going to stop. In the next module, we shall begin to look at how to name enantiomers, and then we look at how this, the polarization, how we can identify if a compound is actually a stereoisomer experimentally in the laboratory. So thank you very much for listening and do enjoy the rest of your day.